video recording reasons. But anyway, I'll begin with a prayer again, just to annoy the internet. No, that's not the main reason anyway. Dear Father, we just thank you again for this opportunity we have. I just pray you'd guide our thoughts in the remainder of this lecture, Lord. In your name I pray. Amen. All right, so now we know the task that's in front of us, right? To solve L of y equals to 0, need y1, y2, yn, linearly independent functions, well, more to the point, solutions, then y equal to c1 y1 plus c2 y2 plus plus cn yn is the general solution to the homogeneous problem, all right? So that was the theorem we got to, right? So the question is, how do we do that? Now, so we're gonna focus on special case because, well, there's good reason to do it. I mean, first of all, most of the known, I mean, many applications fall into this special case, all right? RLC circuits, springs with friction, lots of ordinary differential equations which appear in solving well-known problems in quantum mechanics. I mean, all kinds of things end up being what's called the constant coefficient case. So constant coefficient, nth order, ODE. Now, to be honest, I am combining chapter 4 and 6 in your text. All right? So after we're done with this, we'll be able to solve homogeneous problems either from chapter 4 or chapter 6. There's a lot of discussion of applications in chapter 4, which is probably good for you guys to read, but I don't have it in my heart to lecture on it at the moment. Now, so just to restate the problem, it's this. It's d to the n plus a sub n minus 1 d to the n minus 1 plus plus a2d squared plus a1d plus a naught, all acting on y equals to 0. This is what we want to solve, all right? And so the language we were just using, I have called this thing L, right? But you could also say that this L is equal to P of D, where P is equal to a polynomial, right? P is the polynomial. Let's say I'll write the polynomial in terms of x. P of x is equal to x to the n plus a sub n minus 1 x to the n minus 1 plus plus a sub 2 x squared plus a1 x plus a naught. This is a popular and useful notation. You can take the polynomial of like an operator or a matrix or other things. What that means is you follow the same pattern as the polynomial, just replacing your variable with whatever operator or object you're looking at, in this case the differentiation operator, all right? Let's see here. Maybe I shouldn't use x because I also want d equal to d dx, and admittedly this x and this x down here, like there's really no logical connection between these per se. This is just a placeholder, whereas here I want this to be the independent variable, so fine, that's kind of bad. If I'm really feeling guilty, I might replace this with like lambda or something. All right, enough. All right, so let's talk about operators in calculus, because that's really where it's at. So calculus of operators. Okay, so let T and S be operators, all right? We make the following definitions. If we have T plus S and they act on a function, how does that work? And how about if we multiply T times S? What should that mean? These are the things I need to define. I don't think anyone will get the adding thing wrong. What do you do if you have the addition of two operators? How does it? Exactly. Yeah, we just do pointwise. It's just a T of F plus S of F. Exactly. How about the second one? How does this work? What's that mean, to multiply operators? Now, this is where it might be a little bit surprising. What this means is T of S of F. So multiplication of operators is understood to be composition. All right? So likewise, if I had like T squared of F, what that means is T of F. And I'm not dogmatic on this, but sometimes I write square brackets to try to emphasize that what's going into the operator is a function. All right? This is a legalism I never live up to that long, but you'll see square brackets scattered around my writing. That I'm just emphasizing it's a function that's being inputted. All right? That's a good question. Does ST have to be equal to TS? That's a question. Right? I don't think it does. We'll look at an example of that. That was going to be one of my next examples. Wow. There are actual questions. This is wonderful. And comments? It feels like teaching again. I felt like yesterday and Monday, like maybe I should just stay home and like write on my little table. And then we could all just look at what I did, you know, in the comfort of our own apartments or whatever. But this is better. This is better. So. So, what example am I on? I forgot. 5? It feels like 5. So if we have T equal to, say, D plus 3, all right, and we take T of F, so that would be T squared of F. What does that look like? Let me not do F. Well, yeah, I better do F. Fine. So this is D plus 3 on D plus 3 of F. So what happens when you differentiate? So this is F prime plus 3 times F, right? I guess I should be clear. How's the 3 operator defined? 3 is an operator, and it acts on F at the point X. How? You're like, yay, another level of notation. That's what I wanted. Well, I mean, this is a function, right? 3 acting on F is a function. I'm telling you how it acts at the point X. How does it act at the point X? It's 3 times F of X, right? If you want to strip off the X dependence, you could also write this as 3 acting on F is just 3F. I mean, it's up to you. This is a silly comment, but it's a necessary comment because we do think about multiplication by a number as being an operator. It is an operator, right? So then this gives us what? This is D acting on F prime plus 3F plus 3 acting on F prime plus 3F. So this is going to be what? This is going to be F prime prime plus 3F prime plus 3F prime plus 9F. where I'm using the definition of addition of operators and also just how differentiation works, right? It's linear. I can pull out the 3, right? When we take 2 derivatives, we write f prime prime. Nothing new here. Of course, at this point, you could rewrite this as what? D squared plus 6 times d plus 9, all acting on f, right? Well, that's kind of neat, right? Because this t was really what? I mean, this was really d plus 3 squared acting on f. And so, you know, with an operator, to prove an operator equation, I mean, this has given us, what we've just done, it gives us license to write the following operator equation. We have just shown that d plus 3 squared is equal to d squared plus 6d plus 9. And this is because example 5 held for all functions f. Okay, fine. Admittedly, for functions which are differentiable, it doesn't say, I mean, there is a universe in which this operator works. The absolute value function's not in this universe, for a stupid example. Okay, little proposition. Another example before one more example. We could have t of f equal to x squared d squared, I'm sorry, let me use different notation, x squared f prime prime plus f prime. And we could have s of f equal to f prime plus 2f. Let's calculate what is t s of f then. So we're supposed to do t of, what was s of f? It was f prime plus 2f, right? What was t? It was, I mean, we should probably rewrite this. This is really x squared d squared plus d acting on f, right? So we have x squared d squared plus d. That acts on, in this case, f prime plus 2 times f, right? Now this direction isn't especially exciting. It's, I mean, so the x squared d squared gives me what? It gives me x squared f. I'll write out 2 steps. Fine. D squared f prime plus 2f plus d f prime plus 2f. I'm using the addition of operators definition we just wrote, and this gives me x squared f prime 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 plus 2f prime prime plus f prime prime plus 2f prime, which I suppose I can rewrite as x squared d cubed plus x squared plus 1 d squared that was a 2x squared, wasn't it? Sorry about that. 2x squared plus 1 d squared plus 2d acting on f. I mean, this on its lonesome is not interesting. We're doing this to try to get used to the idea of composition of operators, okay? What happens when we do ST? That's more interesting. So TF is what? It is x squared f prime prime plus f prime, right? But what was S? S was what? It was D plus 2 acting on this, right? So I have, I'll write it out. Let me write it out in the ddx notation since that's a little bit more familiar to you guys sometimes. So I have d squared dx on x squared f prime prime plus f prime plus 2 times x squared f prime prime plus f prime. The 2 operators, not exciting. That part's done. But over here, we've got to be careful, right? We got what? We got a product. See, f is a function of x. X squared, of course, is a function of x. So we got to do product rule. We get 2x f prime prime plus x squared f prime 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 plus f prime prime plus 2x squared f prime prime plus 2f prime. And I'll rewrite that as an operator equation now to finish it up. So I've got x squared d cubed. How many f prime primes do I have? Collecting all my d squared terms, I got a 2x squared there. I've got 1 here. I've got a 2x there. So 2x squared plus 2x plus 1 d squared. Any derivative terms? This one, right? Plus 2d. So you can see that we have, on the one hand, TS equal to x squared d cubed plus 2x squared plus 1 d squared plus 2d. But on the other hand, we have that ST is equal to x squared d cubed plus 2x squared plus 2x plus 1 d squared plus 2d. So, I mean, parts of them match up, right? But in total, they're not the same, are they? Now, you can calculate what's called the commutator. The commutator is this thing. If we do, here's the notation for it, t comma s. All right, so this is by definition ts minus st. And so if you look at what we've just calculated in example 6, we just worked out that the commutator of t and s is actually, if you take the difference of these two, what do you get? Lots of stuff cancels, right? In fact, only we get minus 2x d squared. So in fact, I have this identity. If I want, I could say TS is equal to ST minus 2x d squared. So if I want to commute them, I can't quite commute them, but it's close. I mean, I just have to adjust for this piece. All right.
What's the point of a commutator?
Well, it measures how far from commuting two things are. If it's 0, they commute. In quantum mechanics, it's fundamental. Commutators are everywhere. For example, if you have an operator and its commutator with the Hamiltonian operator is 0, that means that that operator has eigenstates which can be simultaneously measured with energy eigenstates. And there's lots of other things. Like, it's fundamental to quantum mechanics. It's called a Lie bracket more generally. But commutator's good for physics, but for us, it's just sightseeing. All right, the main point here was the calculus that we just did. Now, I have good news. this is much harder than what we're actually doing, okay? But I think it's important to do something like this so you have a sense that, like Isaac was expecting, they don't commute. Now, in contrast, though, example 5, I mean, d plus 3 commutes with itself. That's not a very good example. All right, but let me do a lemma, one of many lemmas here. I should prove. Call this lemma 1. And it states the following: if I have d plus a times d plus b, then that's equal to d squared plus a plus b times d plus ab. I'm saying this is an identity for the differentiation operator and for a and b being constants. Here's the proof. If we have d plus a times d plus b, and they act on a function, let's call it y for a change, well, that's d plus a acting on what? On y prime plus by, right? How's that work? Well, that's, I have to differentiate y prime plus by, and I have to take a and multiply it by y prime plus by. All right, well, that gives me y prime prime plus by prime, because b pulls out because we can pull constants outside of differentiation, right? And then we get ay prime plus aby. And so rewriting this, that's d squared plus a plus b d plus ab, all acting on y. But since this holds for all y, we obtain the lemma. All right? So this one shouldn't be hard to remember. What does it say? You can multiply the differentiation operator and multiplication operator just like they are like polynomials, right? I mean, the usual algebra applies. It's pretty nice. So how about d plus a and d plus b, where a and b are possibly not equal to 0? I'll call this lemma 2. D plus a commutes with d plus b. Here, let's try another one. Do you see? I mean, do I need to prove that? I think it's immediate from this formula, right? Because you can switch the role of a and b, right? A plus b is b plus a, and a times b is b times a. So I can flip-flop them, and I get d plus b and d plus a instead of d plus a and d plus b. So it should be clear that these commute, right? The order doesn't matter. How about this? What if I have d squared plus a1d plus a naught times d plus b. I think you'll believe me when I tell you that that is also d plus b. Well, you know what I should do? Sorry, let me be a little bit more organized here. Wow, fine. Sorry, guys. Lemma 3, how about this? D minus alpha squared plus beta squared this commutes with d plus b. How would we prove it? The proof would be very similar to the ones I've already done, all right? Just feed it a function, and you can show that you get the same thing from both sides, all right? I mean, I can go through it if you'd like. Would you like me to do it? Let me do it. I tell you what, instead of giving you the proof of this, let me show you how it works out for a specific choice of alpha and beta with some numbers in it, okay? Instead of giving you a proof of the lemma directly, let me give you an example which corresponds. Which example is this? Example 7? 6? 7, right? So let's try d squared plus 4d plus 5 and d minus 3, and let's let it act on something relatively harmless like sine of x. All right. So what's that going to give us? The derivative of sine is cosine, and then minus 3 sine of x, yeah? Then this, what do we get? We get d squared on cosine of x minus 3 sine of x, yeah? Plus 4 times the derivative of cosine of x minus 3 sine of x, and then plus 5 times cosine of x minus 3 sine of x. Hey. Man, this is a bad day for me in terms of making examples up. You know, some days. All right, so twice differentiate cosine, you get back minus sine. Twice differentiate sine, we get back cosine, yeah? Idiot. Twice differentiate cosine, you get minus cosine. Twice differentiate sine, we get minus sine. Over here, we get what? Plus. Golly. I should just prove this thing in general. That would have been easier. Idiot. All right. Poor planning on my part. All right. What does that give us? Let's collect our work together. We got a cosine of x. How many of those do we have? Minus one of them here. You're telling me the answer. Minus 12 from this guy, right? And then plus 5. You said that was minus 8. I think I'll buy that. So minus 8 cosine, and then plus sine of x. How many of those do we have? 3 of them here, minus 4 of them there, minus. I think I got minus 16. Okay. In total. Okay, so to summarize, we get minus. Would you tell me? 8 cosine x. Minus 16 sine x. Isn't it funny how much more complicated this looks when you put a specific function in? Like when I was doing derivations over here for arbitrary functions y, it was so much easier, wasn't it? This is the power of abstraction, guys. Sometimes it pays off to be more general, right? As I planned. No, not entirely. D minus 3, but you got to get your hands dirty, otherwise you don't really understand things. D squared plus 4D plus 5. Why? If you work this out, let me just tell you, if you work this out, right? Fine, I'll do it. That's going to give me minus sine x plus 4 cosine x plus 5 sine x. And pays off to simplify before I go on. That's d minus 3 acting on 4 sine x plus 4 cosine x, which gives me 4 cosine x minus 4 sine x minus 12 sine x minus 12 cosine x, also known as minus 16 sine x, yeah, and minus 8 cosine x. Please let that be the same. Ah, yeah, what do you know? They commute. But I hope you appreciate from example 7, saying they commute is not a simple statement, really. When you get into the details of it, we're actually saying something really complicated about the way functions and operators behave. And yet it's simple, right? I mean, it is really simple, but if we flesh it out for specific functions, it is kind of beastly. All right, so I hope I have convinced you by now that if we look at polynomials of the differentiation operator and constants, they behave just like polynomials. So what I'm trying to say is that sort of the uber lemma of this, I'll just call it lemma 4, P of D times Q of D is equal to Q of D times P of D, where P and Q are polynomials with real coefficients, all right? But what I'm really telling you, what that does is it gives us license to factor. We can factor polynomials of operators just like we factor polynomials. That's what lemma 4 basically says, right? I mean, we saw that in example 5 already. We multiply out d minus 3, we got d squared minus 6d plus 9. That's factoring, right? Well, that's not specific to that. I mean, it's generally the case. All right, so now we have finally earned the right to start solving the differential equation. Let me show you how we do it. All right. Lemma 5. Here it is. D minus lambda y equals to 0 has solution y equals to e to the lambda x. Proof. If we take d minus lambda and we let it operate on e to the lambda x, what does that give us? What's the derivative of the exponential? Here lambda is a constant, guys, all right? What's the derivative of e to the 3x? It's what? It's 3e to the 3x, right? So more generally, lambda e to the lambda x. Ha! 0. Hooray. That wasn't too bad, was it? Lemma 6. D minus lambda squared acting on y equals to 0 has solutions y1 equal to e to the lambda x and y2 equal to x e to the lambda x.
What does it mean?
That's a differential equation. Right, I mean, to say that this has solutions means that when I plug that in, it gives me back 0. Does that make sense? Okay. Now, the y1 is almost immediate, right, from the previous lemma. So if we take d minus lambda squared acting on e to the lambda x, what's that do? That's d minus lambda, right, times d minus lambda e to the lambda x. And we just proved in the previous lemma that when we feed e to the lambda x, there's this piece right here, this is 0 by lemma 5. Yeah. Fun fact, if you feed the linear operator 0, guess what you get back? You get back 0, all right? These polynomials in the differentiation operator, these are all linear operators, all right? So this is 0. So again, woohoo, y1 is a solution. How about y2? How's that go? X e to the lambda x. What happens there? Remember what multiplication is composition, so it means we gotta do e to the minus lambda 2 times. Yeah. What happens with the first application? Well, we already did that in the lemma 5 calculation, right? We already know what this works out to, right? Been there, done that, kind of. Well, I'm sorry, I'm not being entirely honest with you. Fine. What's the d on that product rule, right? X times e to the lambda x is a product. So this gives me e to the lambda x plus x lambda e to the lambda x by the product rule. And then we do what? We subtract multiplication operator lambda x e to the lambda x. See what happens then? The x lambda piece cancels. So we're just left with what? E to the lambda x. But we already know from lemma 5 that this guy kills it, right? So we get 0, which shows you that y2, that function, when you plug it into d minus lambda squared, gives you back 0. In view of this theorem, this shows you the general solutions to the differential equation in lemma 1 and lemma 5 and lemma 6, right? So if you can do it for a second power, you can do it for a first power, why not do it for the kth power, right? So continuing, lemma 7, I'll just jump ahead a bit. If we have d minus lambda to the, let's say, kth power, y equals to 0. So this is a kth order differential equation with constant coefficients. This has solutions y1 equal e to the lambda x, y2 equals to x e to the lambda x, and so forth and so on down the line. Yn equals to x to the n minus 1 e to the lambda x. So I'll only show you, I think if I show you y sub n, did I say n? I'm sorry, I put a k up here, I put an n down here, I can't make up my mind. better. Let's look at why the last one is a solution. The proof that everything up to the last one is a solution is very similar to lemma 6 rather. So it's almost the same thing again, though. So what's that going to be? That's going to be d minus lambda to the k minus 1, and then d minus lambda acting on this thing. How's that work out? Product rule gives me k minus 1, x to the k minus 1, e to the lambda x minus, or excuse me, plus lambda x to the k minus 1 e to the lambda x. That's all just from differentiating the product there. And then, of course, I have minus lambda x to the k minus 1 e to the lambda x. You notice the highest power x terms cancel again, and what are you left with? So you're just left with this piece, right? So this calculation shows that that's 0 by induction. Do you guys know induction? Do you know how to do induction? Anybody know? We suppose something is true for, like, in this case, the kth power. Actually, so here the induction step would be, suppose true for k minus 1, goal, show true for k. All right, so like, assume inductively that this lemma holds for k minus 1, for some integer, some natural number k minus 1. Then we look at the kth one, which is what I'm calculating here. Calculate the kth one, these things cancel, we're just left with this. But then I know that this is 0 by the induction hypothesis because this is the k minus 1, 1. Basically, it's just a formal way of extending this bootstrapping that we've already seen going on here. So if you don't find this convincing, watch a previous semester. It sometimes goes better than it happened to just now. All right. So, hey, that's, so if you think about factoring a real polynomial, well, let's solve some problems. I think we have enough to solve some problems. Let's do that. I suppose there's one more lemma I need. Lemma 8. If L1 of y is equal to 0, or let's say L sub j is equal to 0 for some j in 1, 2, let's say n, then L1, L2, Ln of y is equal to 0. Now here, the reason, and I want to assume that these are commuting operators. If we have a set of n commuting operators, then if even one of them makes y go to 0, it means the product of all of them makes y go to 0. The proof is very silly. It's just this, L1, L2, Lj is somewhere in here, all right? if you let that act on y, if these commute, what can you do? You just bring Lj to be the first one, right? Let it act on y. We're assuming that it's 0, right? And then the thing is, this is again a linear operator, and if we feed a linear operator 0, we get 0. This is important because it means that we can divide and conquer. When we have a polynomial that has more than one kind of factor, it suffices to figure out what happens with each different factor, and then we can solve. All right, so let's actually do some. So what I'm thinking what we're going to do here, guys, is I think, when did I, what minute am I in there? Can you tell me what the timestamp says? I'm sorry. Okay, cool. All right, excellent. So I think I'll try to do real examples here for the rest of this arc of our lecture, and then after the break, we'll do the complex case. Okay? So I'm deliberately avoiding complex things here for a little bit. What example am I on? I'm on example 8? Okay. All right, here we go. You guys should like what's about to happen. So let's solve y prime prime plus 7y prime plus 8y equals to 0. Here's what we do. This is d squared plus 7d plus 8 acting on y equals to 0, right? But by the lemma I just erased, we can factor, right? Can you factor that? Oh, this is a right that I have that you don't have. This is an important right for me, but it's the right to do this. It's a very important step. Because one is fun to factor and the other one's not. The juxtaposition of the 7 and 8 there is important. See, because now I can factor, right? What is the how do you factor? D plus what? What did I say? I heard a 7 and what? 1, right? You multiply it out, you get a 7, and you get a 1, so you get an 8. There we go. So what I'm doing, guys, is I'm thinking of this as my L1. I'm thinking of this as my L2 in lemma 8. All right? You see that? I mean, that's the idea here. I'm thinking of those as the operators. And by lemma 5, we know that L1 of e to the minus 7x is equal to 0, and L2 of e to the minus x is equal to 0, right? By lemma 5. Don't worry, I'll stop talking about the lemmas before too long. I'm just trying to make sure we understand the logic here. Because you are going to need to use this logic backwards tomorrow in what's called the Annihilator Method. I only spend time in a proof in here if it's for a larger purpose. I don't do proofs just for fun. I mean, there's lots of proofs that are more fun than the ones I'm showing you. So if I was going to do ones for fun, rest assured, they wouldn't be the ones I'm showing you. These serve a larger purpose, which is calculation. Anyway, so definitely a solution to the pieces of the operator, right? By lemma 8, e to the minus 7x and e to the minus x are solutions to the differential equation. By the theorem I wrote over here, what's the general solution then? All right. C1 e to the minus 7x plus C2 e to the minus x. There you go. Check it out. No reduction to order and no v dx integration, right? Just straight algebra to the solution. If you can factor quadratic equations, you can solve these. But you need to factor quadratic equations correctly and carefully. That is where students lose points here. I mean, I don't want to say you're just like previous students have taken this class, but, you know, I mean, isn't math just a large collection of stereotypes? You're like, I'm looking at the exponential function. You're like, but which exponential function? Surely we can't say all exponential functions are the same, or it's not like there's just one exponent. You know, there really is just one exponential function. I'm sorry. It's part of the reason well, I have to be careful. You never know when politically correct things, incorrect things become actually troublesome. Let's see here. It's always this moving goalpost. All right, example 9. How about this? Y prime 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 plus 3y prime prime plus 2y prime equals to 0. All right, I'll pick up the pace a little bit here. This is d cubed plus 3d squared plus 2d acting on y equals to 0. All right, so that is d times d squared plus 3d plus 2 acting on y equals to 0. Can you factor that? Yeah. So this is d times d plus 1 times d plus 2 acting on y equal to 0. And so a convenient shorthand to express what I did in the previous example would be that this is lambda equals to 0. This is lambda equals to minus 1. This is lambda equal to minus 2, right? Therefore, my general solution is y equal to, what we got? Looks like we got a c1 e to the 0 times x, yeah, plus c2 e to the minus x plus c3 e to the minus 2x. Now, of course, we should be civilized. Let's rewrite this in a proper way. C1 plus C2 e to the minus x plus C3 e to the, I mean, it is expected that students know that e to the 0x simplifies to be 1. Not writing 1 there will probably cost you something. Writing sign of 0 rather than 0 will probably cost you something. I'm trying to fix these things for you. Maybe it's too late, but we should know certain things at this point. Sine of 0 is 0. Cosine of 0 is 1. E to the 0 is 1. Things like this, yes. Anyway, there it is. General solution. Third order problem. Three constants in there. Should we do another? These are fun, aren't they? I mean, you're like, well, maybe. Depends on your idea of fun, I suppose. But, I'm going to mix it up a little bit. Let's solve d squared minus 1 squared times d plus, times d plus 1 acting on y equal to 0. All right, so let's see here. What is that? That's actually d plus 1 times d minus 1, isn't it? So what happens when we square a product we get? Looks like we got d plus 1 cubed. We've got d minus 1 squared. So let's see here. What's going on? So this one gives me three things. It gives me e to the minus x. It gives me x e to the minus x. It gives me, what else? It gives me x squared e to the minus x. All of those come from the first factor. The first factor will become 0 if we evaluate it on any of those three functions. And those three functions are, in fact, linearly independent. The other one gives us what? This was lambda equals to minus 1. This over here is going to be lambda equal to 1. What did you say? Oh, no, no x cubed. No, no, no. These are different lambdas. E to the x and x e to the x, right? And that's why I did this example, because I want to free you of that idea that it's x cubed. They're not intertwined, right? So what you got to do is you got to factor the polynomial into distinct linear factors. You group all of the linear factors together. Once you do that, then you can use lemma 7 to write down the solution that corresponds to that factor. And then you do that for each distinct factor, put it all together, that gives you the general solution. So here the general solution is c1 e to the minus x plus c2 x e to the minus x plus c3 x squared e to the minus x plus c4 e to the x plus c5 x e to the x. Yeah. Yep.
So if you had written it in reverse order, like it goes e minus 1 squared and then e plus 1 cubed,
Yeah.
would your constants be different, and would that be wrong?
It would not be wrong. You could take this and rewrite it as 5 and rewrite this as 1. It wouldn't change anything. Yeah. There's always a labeling degeneracy. That is true. All right, we take a 5-minute break, and then I'll start again and show you how to do it when it's complex, because polynomials don't have to factor to real ones, right? We could also have things like irreducible quadratics. But anyway, yep. 5-minute break.